Okay guys, so today we're going to be doing 6.1 exponential growth and decay functions. So this shouldn't be anything new to you. You should be, well, you learned it in Algebra 1, but hopefully you remember something of what you learned. It's going to make your life a little bit easier during this lesson. But if not, I am going to start from scratch just to be sure. It is actually a really good time to learn this lesson right now because exponential growth models is what they are using to describe the coronavirus and COVID-19 and everything. So if you hear those words, maybe this will help you understand what they're trying to say a little bit better. So the first example is analyzing exponential functions. So I have two graphs here. I have one where the graph is going up and one where the graph is going down. Hopefully, as you can see, the graph going up would be exponential growth and the graph going down would be exponential decay. So growth, something gets larger, decay, it whittles down, smaller. So they use the same exact equation, y equals a times b to the x power, but they have different criteria, where growth, the b value has to be greater than 1, and decay, the b value has to be between 0 and 1. So a decimal, a fraction, but it's not always a decimal and fraction. If the decimal and fraction, such as an improper fraction, is greater than 1, then that's actually growth, so just be careful with that. So the first examples that we're going to do says, tell whether the function represents growth or decay. To save time, I'm not going to write that part out. So the first one is y equals 4 to the x. Now in that problem, there is no b. So you're looking at just a number that's exponentially getting bigger. So that one is going to be growth. Okay. And then we have number 2, which is y equals 2/3 to the x. Okay, 2/3 is a fraction that's between 0 and 1, so that is a decay. All right, let's do 2 more of those. Okay, so then we have a third example, which is f of x. Remember, f of x and y are literally the same thing. Don't freak out. 0.25 to the x power. 0.25 is a decimal between 0 and 1. So since it is a decimal between 0 and 1, it is a decay. And last but not least, we have, let's use f of x again. .5 to the x. So 2.5 is a decimal, but it's greater than 1. So it's growth. And one example done. Okay, so a lot of times you'll use these in graphing. I'm not going to do graphing with you guys because I know it's too difficult right now to teach you graphing from home, and most of you will just use a calculator and not actually learn what you're doing. So I'm going to skip the graphing portion of it because you will relearn it in your other courses that you're going to take next year. And I'm going to go right into using exponential models because you will see that again. Okay, example 2, exponential models. All right, so this is probably the most important one and the one you'll see the most, and you did definitely do this one in Algebra 1. So we have growth versus decay, and our growth formula is y equals a 1 plus r to the t, y equals a 1 minus r to the t. So you can see they're pretty much the same. This is 1 plus r to the t. This is 1 minus r to the t. So growth, you're adding the percentage, and decay, you're subtracting the percentage. So let me just let you see, tell you what those mean. So y is obviously your population or whatever you're finishing with, where a is your starting value, r is your rate, but you have to change the rate to a decimal. We can't put just percentages into a formula. And t is time. Time is usually in years, so that will help out with that too. All right, so same thing. I'm going to just read out loud the word problem because I will post my notes online after I finish with the video. So I'm just going to read the word problem and I'll write the information on the board. Okay. So the value of a car Y in thousands of dollars can be approximated by the model. Y equals 25 times 0.85 to the t power. So that's the model of the car and the value that it has. Where t is the number of years since the car was brand new. So first things first, is this a growth or is this a decay? So I'm going to look at my percentage here. This percentage is less than 1. So it's going to be decay because 1 minus. If it was a growth, it would be greater than 1. So growth is greater than 1, decay is less than 1. So this is a decay. And obviously that makes sense because unless you have a classic car, the older it gets, the less that it's worth, right? Okay, part B says identify the annual percent increase or decrease. So we already said it was a decay, so we know it's going to be a percent decrease. So since it's a decrease, I'm going to take that formula here, the 1 minus r, and I'm going to equal it to the percentage they gave us. And I'm going to solve for the rate. So I'm going to subtract 1. 0.85 minus 1 is 0.15. To get rid of that negative, I just divide by a negative. So that gives me 0.15, which is a 15% decrease. Okay. And then it says estimate the value of the car after 4 years. So all you have to do is plug 4 into the formula for t. So I have y equals 25, 0.85 to the 4th, because this adds are 4 years. And we get 13. We get 13.050156. Now, it said in thousands from the beginning of the word problem. That's not in thousands. So I'm going to times that number by 1,000 so I can get my actual value. And I get $13,050, and rounding it up, 16 cents. So that's example 2. And sorry, I just realized you couldn't see that all the way. And that's it for that one. That's going to be one of your most common ones. So if this was a growth model, you would do the exact same thing. This would be greater than 1. You would say this was a growth. Then you would plug this part into whatever the percentage was to get the percent increase. And then you plug in whatever value that they give you to find the value or the population of whatever they want. Okay. Example 3. Okay, writing an exponential model. I'm going to abbreviate that. Okay, writing an exponential model. Same thing. I'm going to read the word problem out loud and go from there. All right, so in 2000, in the year 2000, that's our starting year, the world population was about 6.09 billion. Okay. During the next 13 years, the population increased by 1.18% each year. Write an exponential model giving the population y in billions t years after the year 2000. Estimate the 2005 population. So first things first, in order to write a model, I need to know, am I writing a growth model or am I writing a decay model? It said increase, so we're writing a growth model. So let's start with our original formula. Let's remind ourselves of that. It's growth, so I'm going to put the plus R. And now I'm just going to fill in what I know. I know my starting point was 6.09 billion. 1 plus my rate. Now this is my rate, 1.18. But I have to turn that into a decimal. So for those of you that don't remember, you have to move 2 decimal places to the left. So 1, 2. Which gives me 0.0118. Right? And then I don't know t as of right now. I'm just writing the model right now. So my model is y equals 6.09, 1.0118 to the t. Right? I just abbreviated. Now it said find it, estimate the 2005 population. So 2005 is 5 years after 2000. So that's what I'm going to plug in. So to the 5th. And I'm just going to plug that into a calculator, which I have already done. And you get 6.5 billion. That's it. Now, if this was a decay problem, all I would do is switch this to 1 minus R, fill in my information, simplify, and plug in. That's all we're doing. Pretty simple. Okay, we're at the last example for the day. Okay, example 4. Which is finding the balance in an account. So something you can use in real life. Okay, so this is what we call the compound interest formula, if you've ever heard of it. So, which you should have because you did it in Algebra 1. You know, this is really where I miss you guys saying, oh, I was never taught this. So, the compound interest formula is A equals P 1 plus R over N to the N times T. Okay, where P, well, A is the amount of money afterwards, like once you finish. It's always what an equation equals. P equals your starting money, your principal. I like to call it start money. R, same thing, is your interest rate. N is the new one here. That's the number of times compounded. Okay, the number of times compounded. T is time, as always. But I want to talk about that compounded. So that can be a lot of different things. So if they say biannually, that's twice. Semi-annually, twice. Quarterly, 4 times. Monthly, 12 times. Weekly, 52 times. Daily, 365 times. So you guys just have to make sure you understand your vocabulary to know how many or what number to plug in for N. So again, I'm just going to read what we're doing and we'll use that formula to apply it to the word problem. So it says you deposit $9,000 in an account. $9,000. the account pays 1.46% annual interest. Right? Find the balance after 3 years. If the interest is compounded quarterly, which we know quarterly is 4 times. So all I do is plug all that information into the equation and put it into the calculator. So A equals 9,000 times 1 plus 0.0146, because we have to convert that percent, over the number of times compounded, which is 4, to the 4 times 3 years. So you can simplify, or you can just plug it into the calculator just like that. When you plug it into the calculator, you should get $9,402.21. So $400 in 3 years just in interest isn't bad. All right, guys, that's it. If you have any questions, please reach out as soon as you have them. Don't stay stuck on a problem. I will gladly answer your questions as you need them. Homework will be posted in the instructions. Okay, thanks.